Radioactive decay is a process in which a radioactive isotope changes from one isotope into one or several other isotopes. So you have some parent nuclei that decays into a daughter or several daughter nuclei. This process is a statistical process, meaning that the individual change of a parent nuclei into a daughter nuclei is not known when that will occur. It's a random process. It's very much like flipping a coin. You don't know beforehand if a coin will definitely land heads or definitely land tails, but you know that if you flip 100 coins, you're likely to have about half of them heads and about half of them tails. Which particular coin will land heads and which particular coin will land tails, you can't predict. But statistically, you can be pretty sure that about half of any number of coins you flip will be heads and the other half will be tails. So radioactive decay occurs when half of the parent nuclei decay in a given time frame. How long depends on the element or isotope we're talking about. Some isotopes decay incredibly quickly and others decay very, very, very slowly. But it's a fixed value for a given isotope. Uranium-235 has a fixed average time where a uranium-235 nuclei will decay. Carbon-14 has a fixed time where a carbon-14 nuclei will decay. So this time is called the half-life. The half-life is usually represented by T with a subscript of 1/2, because it is a time. So each individual isotope, each particular type of isotope has a unique half-life. So carbon-14 has a half-life, and we can talk about what that is. Uranium-235 has a half-life. Uranium-238 has a half-life. Plutonium-239 has a half-life, and so on. Each one separate from the other isotopes. If we want to know, for a given amount of time, how many isotopes we have left. So if we start off with a fixed number, N0, it could be 100, 1,000, a billion, whatever. How many isotopes remain, N, is given by the equation, N equals N0, the number of original isotopes, E to the minus lambda times time, where E is not the charge on an electron, we've used it before, the charge on an electron, that's the base of the natural log. So it's just a number. Your calculator will have probably a little e to the x option. That's what we're talking about here. The base of the natural log. E is 2.71828 and so on. It's an irrational number. T is the amount of time you want to know that has passed. This is not the half-life here. This is just time. So if we want to know how many remain after a day, or after 100 years, or after a billion years, that's the time we plug in. And in this equation, lambda is what's called the decay constant. Now, we don't use half-life in this equation, as you can see, but lambda is related to the half-life. So if you know what the half-life is of an isotope, you can find out what the decay constant is of that isotope using the following equation. The natural log of 2 divided by the half-life gives you the decay constant. So the decay constant will have units of inverse seconds, or seconds to the negative 1 power. So when you have seconds to the negative 1 times seconds, those units cancel, and you have a unitless power here, which is what you want. So the number of particles on the right-hand side is a unit here, then on the left-hand side you get number of particles. So if we figure out, if we're given a half-life, we can use it to find the decay constant, plug in the time with that decay constant, and we can figure out how many particles remain. Now this is very useful for the point of radioactive dating. And we work out some example problems, and you can look at some of the problems that I've put online. Radioactive dating is a very useful technique in dating the age of the Earth, in dating the age of antiquities. If we pull up, for example, in Pompeii, when the volcano went off and buried the city, we can radioactively date the fossils we find, not really fossils technically, but the people, right, that we find that existed 2,000 years ago that were buried, the wood that was cut down, the paper that they might exist. We can radioactively date these using typically carbon-14 dating. and get an age for these events. So again, look at the example problems that I do, and you will have homework problems dealing with radioactive decay. Now, carbon-14 dating, which I mentioned just a bit ago, is an important way of dating organic materials. So in our lives, as we consume food, plant or animal matter, doesn't matter if you're a vegan or an omnivore, you eat carbon-14. Carbon-14 is produced in the upper atmosphere and is absorbed by plants as plants inhale carbon dioxide and exhale oxygen, or through that process of photosynthesis. So carbon-14 is constantly replenished in plant life, and then of course animals eat the plants, humans eat the plants or the animals, or both, and then get carbon-14 brought into their system. So daily you are replenishing the amount of carbon-14 in your system. When you die, or when an animal dies or a tree dies, it stops bringing in new carbon-14. So the carbon-14 that exists in the animal or plant slowly decays with time, and the decay rate is 5,730 years. So that is the half-life of carbon-14. So after 5,730 years, the amount of carbon-14 a plant or an animal has is cut in half. After another 5,730 years, it's cut in half again, and then again, and then again, and so on. So if you start off with 400, for example, 400 carbon-14 atoms, after this amount of time, 5,730 years, you'll have 200. Then after 5,730 years, you'll have 100, then 50, then 25, and so on. Eventually, you can only go back so far. Carbon-14 dating with modern technology, I believe, goes back 30 to 40,000 years, which means that material older than 30 or 40,000 years cannot be dated via this method because too much carbon-14 has disappeared. Now, carbon-14 having a half-life of 5,730 years also means for an individual atom that for this carbon-14 isotope, there is a 50% chance that it will decay before 5,730 years. And there's a 50% chance it won't decay in that amount of time. So you flip a coin. Does the carbon-14 decay or not? After 5,730 years, if you still have your carbon-14, if it hasn't decayed, then in another 5,730 years, there's a 50% chance it might decay again. So you can't predict individual atoms and how they'll decay over their half-life. There's a 50% chance they'll decay before one half-life, and a 50% chance they'll decay after that half-life, some point afterwards. So we have to look at this as a statistical process by looking at a large sample and then seeing how the decays occur. Now, another way of looking at radioactive samples is you have, again, isotopes that are decaying, giving off alpha, beta, or gamma rays, or giving off other particles. So we want to look at what the activity rate is. How active is a radioactive substance? Activity is in number of decays per unit time. Remember, alpha, beta, and gamma particles can be damaging. So if an object or if an isotope is very active, it has a high activity, it is a dangerous thing, or can be a dangerous thing. If it has a very low activity, it's not particularly dangerous. So we want to look at the number of decays per unit time. So the rate, or the activity rate, is the number of decays per unit time. Then going back in and plugging in the equation we had, we can see that it's equal to 0.693 times the number of particles over the half-life of those particles. So it depends on two things. How many particles do you have? Clearly, if you have twice as many particles, you're going to have twice the number of decays because twice as much will decay. And it depends on the half-life. Big half-lives means small activity. So something that has a half-life of 1 billion years is much safer than something that has a half-life of a few seconds. Now, units for activity, Becquerel, I'm mispronouncing that, I'm sure, BQ, where 1 BQ is 1 decay per second. This is also this is the SI unit for decays. Decay rate, 1 decay per second. There's also a decay rate called the Curie, named after Marie Curie, who did a huge amount of work in early understanding of radioactive substances. Where 1 Curie is 3.7 times 10 to the minus 10 becquerels. So, becquerel. I'm sure I'm mispronouncing that. If you know what the decay rate is at a particular time, and you want to know what the decay rate will be in the future, for instance, the radioactivity, the activity of the substance is dangerous now, at what point in the future will it not be dangerous? The rate in the future is equal to the current activity rate, e to the minus lambda times t, where lambda again is the decay constant for that isotope, and t is the amount of time that has elapsed that you're interested in knowing what the rate is. This is not half-life again, this is just time. The half-life is actually in that decay constant, where the decay constant is equal to the natural log of 2 over the half-life.